Hi, it's time for another math easy solution. To discuss a pretty interesting topic, and that's on Euclidean division, and look at the theorem and then derive the proof of it, or go over the proof. So let's just jump right into Euclidean division. Let's look at the Wikipedia mainstream view of it, and then just go over the derivation. So Euclidean division in arithmetic. Euclidean division is a process of division of two integers which produces a quotient and a remainder. This is a theorem that states that the quotient and remainder exist and are unique under some conditions. Because of this uniqueness, Euclidean division is often considered without referring to any method of computation and without explicitly computing the quotient and the remainder. The methods of computation are called integer division algorithms, the most well-known being long division. And going further, Euclidean division and algorithms to compute it are fundamental for many questions concerning integers, such as the Euclidean algorithm for finding the greatest common divisor of two integers, and modular arithmetic, for which only remainders are considered. The operation operation consisting in computing only the remainder is called the modulo operation. So the modulo, like I've done in my earlier videos on the Tindry series, it's used to find the remainder. So anyways, just to give an example of Euclidean division, if you had a pie here, so the pie has 9 slices, so each of the 4 people receive 2 slices and 1 is left over. In other words, so we have 4 people here. Now we have 1, 2, 3, 4, 5, 6, 7, 8, 9 slices. So if we divide this 9 sliced pie by, I'll just put it over here. So 9, actually make this smaller so we can see. So we have 9 slices of pie divided by 4 people. This, you could writing it as this. I'm just going to move this up here and move it here. So 9 divided by 4, well, you could also just split this up into 8 plus 1 just to show you different ways of getting this Euclidean division. I'll get to that the algorithm in a bit, but this is the way I like doing. Just break this up into 8 plus 1 is 9. So we have like this, and we divide that out. We get 8 divided by 4 plus 1 over 4. In other words, this equals to 2. 2 plus 1 over 4, and what we have now is each person gets 2 here. So that is our 2. And then we have 1 left over for 4 people. So 1 out of 4 there. So everyone gets 2, and then you could think of it as a quarter of 1. So each one would have to get this in 4s like that. So now that we have this, I'll revisit this in a bit. So that's just to give you an idea how you could break this up into a quotient, and the remainder is actually going to be the 1. So that's the 1 there, So going further, statement of the theorem: given two integers a and b, with b is not equal to 0, there exists unique integers. So the exist and the unique we need to prove. Integers q and r such that a equals 2 b times q plus r, and r is between 0 and less than absolute value of b, where b, the absolute value, denotes the absolute value of b. The 4 integers that appear in this theorem have been given the names. A is called a dividend, and b is called a divisor. So you're dividing a, the dividend, by b, the divisor, and q is called a quotient, and that's the result, and r is the remainder. So if you go back up to here, so in this case we have the dividend a is 9, so then we have divided by the divisor b. This equals to q is the quotient plus the remainder is r, and then divided by that b again. And if you multiply the b out on both sides, what we end up getting is a equals to b q plus r, like that, r, or I'll just put it lowercase because that's what the Wikipedia uses. So lowercase r, like that. So this one is exact same form as this one, and we have, well, b is not equal to 0, so we can't divide it out by 0, you go to infinity. So anyways, going further, that was just to give you an illustration of it and just to show you how this works. And also, as you can see, going back here, the r is going to be, well, you're dividing it by b, but the quotient includes all the whole numbers there of 4 here. So we have 4, and this one is 1, so then this one's always less than 4. So then we have r is less than or equal, just less than the absolute value of b, and greater than or equal to 0 here, because you can have a 0, you can have negative in this case. And if you have a or b negative, you could actually play around with it to make it r positive. So anyways, we'll go further into this. So going further, the computation of the quotient and the remainder from the dividend and the divisor is called division, or in case of ambiguity, Euclidean division. And the theorem is frequently referred to as a division algorithm, although it is a theorem and not an algorithm, because its proof, as given below, also provides a simple division algorithm for computing Q and R. So the proof is in the algorithm. It's pretty interesting. So division is not defined in the case where b equals to 0. See division by 0, because then you have a over 0 approach as well. Infinity, or undefined if a is 0. So undefined, like that. Now for the remainder and the modulo operation, there are other conventions than 0 is between r and b. And you can play around with it. You can make r, because r and q are going to be intertwined depending on what q is, as I will illustrate soon. So let's look at this proof. Or even actually, before I get to the proof, I just want to go with some more examples. Let's put an example here just to give you an illustration how r and q are intertwined. So example, if we have, let's say 9 divided by 2, and let's just throw a negative sign in there. So negative 9 divided by 2, like this. Then what we have is, what we could do is we could break this up into negative 8 minus 1, so that adds up to negative 9 divided by 2. Divide this out just to give an illustration. This becomes negative 4, and then this part here is negative 1 over 2. And just to show you how we can have different quotients and remainders. And this isn't the division algorithm, this is just my little way of dividing here. Now in this case, when we multiply by the 2, well, let's put this over this side, negative 9 over 2, just to show you. What we could do is multiply both sides by 2, so what we end up getting is negative 9 equals to negative 4. Before I'll just put the 2 in front. So 2 times negative 4, like this, and then minus 1, because this 2 cancels there. And now the problem is over here, if this equals to b, q, and then plus r, what we have in this case here is the remainder is basically r is less than 0. But we want r is greater than 0, just to show that that theorem still works. And you could actually do that. You could actually change the quotient here. So initially q is equal to negative 4. So what we'll do is instead, what we could write it as instead, just to get a positive remainder. So negative 9 over 2, this equals to, same thing as writing negative 10 plus 1. So instead of doing that, just to show that we can still get that remainder is positive, divided by 2. This equals to, now this becomes negative 5, and then negative 5 plus 1 over 2, multiply by 2 on both sides, we get negative 9 equals to 2 times negative 5 plus 1 right here. And now what we have is, in this case we have over there, put the arrow this way, so q is equal to negative 5, and then r is equal to 1, which is greater than 0. Then it's less than 2, as it should. So very interesting. You could basically have it so you have r different. That's why there's different conventions for what r can be. And in this case here we have this one was q is equal to negative 4. So if q is different, r is going to be different, and so on. So now let's look at the formal proof by Wikipedia that they have, and then they don't illustrate it pretty well, so that's why I'm doing this video. So let's look at the proof. So the proof consists of 2 parts. First, a proof of the existence of q and r, and second, the proof of the uniqueness of q and r, to show that q and r are always going to be unique. And that if you scroll up here, as this example I did, this one, the q and r's are different, but the thing is, this one is not r is greater than 0, so you can't have 2 different q's and r's when r is greater than 0. This one is r is negative, so when it's negative, then you can change things up. So I would assume actually that there'll be a unique one for negative side and the positive side. That's my hypothesis. I didn't look into that too much, but I think it is. So let's go first, look at the existence. So number 1 existence right here, or existence of Q and R right here. So let's look at the case where we have B is actually less than 0. When B, the divisor, is less than 0. So what we'll do is before I get to this, I'm just going to do let B prime like that, or B dash number, the one across there, I'll call prime. So B prime equals to negative B. So when we do this, just to show you that this is a negative of a negative number, this is always going to be greater than 0. So when we do this, and then if we write that down as A equals to, well, we have the B is going to be negative B here, just replacing the B, and this is Q plus R, like that. Just replacing the B with negative one there, but then if we put a negative just so it's positive, the same thing as writing B prime Q plus R. And likewise, this is for 0 is less than, and now we'll do R less than equal to, and then the absolute value of, well, negative B is the same thing as writing this equals to B prime, because we're looking at the positive side, and a negative of a negative number is going to be positive. So then this means that thus what we have, this problem is all we're doing is changing the variable. So we have thus A equals to B prime Q plus R, and this is for 0 is less than, this is for this kind of remainder convention like that. This is going to be B prime. So what we have here, notice what we have here, all we've done now is we've reduced this, because B prime is greater than 0, so then we've reduced the case of B less than 0 to just a case where it's greater than 0. So thus we reduced the B less than 0 case to, well, B is greater than 0. This is B prime, it doesn't matter what it is, it's just another variable. You can write Z if you want. So that's just the same exact theorem that we had. So now we got to work with just B prime, just B is greater than 0. So it's very actually fascinating kind of proof in my view. So let's look at this case. Let's look when B is greater than 0. So our case B is greater than 0. But now what I'll do is B is greater than 0. I'm also going to put the other condition where A is less than 0, just to get rid of all the negative A and B's, and then I'll show you it's all the same for positive. And now we'll do the same thing. I'm going to do is let A prime equals to negative A, so that this is now positive. And now if we write that in the equation for the basic A's like that, but now we're doing a negative of everything, this is going to be equal to negative, and then BQ plus R, expand this out, is equal to negative BQ negative R. And this is because when we do A divided by B, we're going to need to have negatives everywhere where B is positive and A is not. But notice what we have here. If we let, I'll write here if, or if we let, just to make it written in this form, if we let negative R, or R prime equals to negative R here, and also Q here, Q prime, I'll just put an arrow or just comma like that, and Q prime equals negative Q like that. Thus what we have is A prime equals to, now we get rid of these negatives there, B Q prime plus R prime. But now the problem is this is for 0 is less than equal to R prime, and this is, well, less than B, because B is always positive. But the problem here is this is negative, so then this we can't do. Put a big X like that, and this is because can't do because R is negative. So it's because R is actually less than, or R equals to, or R prime equals to negative R, where this is going to be less than 0. And this is because we've been always working with the condition that R is always just greater than 0. So we can't do this method there, but what we can do now is let R prime and Q prime be something else. So what we'll do is try, instead, I'll do it again, I'll still let A prime equals to negative A, But now I'll, instead of I'll just try this one instead. And now what I'll do is I'm going to start off here, negative bq minus r. I'm going to split that up. So I'm going to do negative bq. And I'm going to do is subtract this by b and then plus b, so we're not changing anything, r like that. And then the reason I'm doing this is if you subtract or take the b out of this, what we end up getting is b, just get that out, and then we have a negative q minus 1, factor that out. Now this side here is plus b minus r like that. And number r is between b and 0, and b is always greater than 0 is the case we're looking at. Then this, what we could do is let this equal to r prime, and this is going to be less than b because you're just subtracting it. And then what we'll do is let this part equal to q1 or q prime. Yeah, so now we've got rid of that case, or sorted that one out. Now what we'll have is, again, so now we'll do is let q1 equals to negative q minus 1, and we have r prime equals to b minus r, and then when you put that in, it becomes this negative bq, because again those just cancel. It's the same thing as negative bq minus r, and so on. So thus what we have now is we're able to reduce this whole problem even further. So thus a prime equals to, and then we have bq prime, and then plus r prime. For r is going to be, we define, or we're letting it as being positive, greater than or equal to 0, less than now b, because that's how the remainder is supposed to be. So there exists, well, we'll show that soon. But what we've done now is, well, we've taken this negative a, or a is less than 0 case like here, but now what we've done is change it up where now this part right here is greater than 0. Now the a prime is, because we're putting a negative there, so let a prime equals to negative a, which a is negative, so two negatives become a positive. So thus what we've done is what we've done is reduced the, or instead of saying reduced, I'll just write reduced to just, now what all we're left with is now a is greater than or equal to 0, because a could be 0, 0 divided by whatever is going to be 0, as long as it's not 0, as long as we're dividing by 0. So now what we're just left with is a positive a, and also b is greater than 0, and this is all we need to work with, positive integers. In other words, positive integers like this, like 3 divided by 2 and so on. So it's, yeah, so very, very interesting. We've reduced the whole thing just by rearranging it to show that it's all the same as trying to prove this one thing. Yeah, so now what we'll do is just need to look at that case. So case here, a is greater than or equal to 0 and b is greater than 0. And also what I'll do is I'll show the division algorithm which is used in the proof of their existence. Or division, I was thinking that and typing something else. I mean, I was thinking algorithm, but I was thinking proof, but I was saying algorithm. Alright, so let's go with this derivation, but first I just want to show that a, now we have positive integers, so a divided by b is going to be greater than or equal to 0, because it's these are all positive values. And so thus what we have, or what we should have, is a over b. You could think of this as quotient plus remainder divided by b. Just split that a up into it, and this is going to be greater than 0, and that q and r is going to be greater than 0. So q and r are greater than 0. So we'll assume this exists. So now what we'll do is look at the division algorithm like this. Algorithm like this, and I'm just going to circle this. And what I'll do is I'll make a table like this. So I'll make a table, and I'll put this as number. So this will be number 1, 2, 3, or just a sequence of events like this all the way to k, and so on. And now what we'll do here, I'm going to write this as value of q. Initially q, I'm just going to let that equal 0. So these are, q and r have to be greater than 0. So q is going to be start off at 0, and it's integers, so we have to go by whole numbers. So if q is 0, then the second one I'm going to go 2, 3, 1, 2, 3, and so on right here. And this is, as you can see, this is just k minus 1 over here, 1, 0, 2, 1, and so on. That's just number of row. And now what we have is, look at the r values. So r, the remainder is just rearranging of the formula. Well, a equals bq plus r, and then rearrange this over there, and then throw this down over there. So we have r is equal to a minus bq, like that. So what we'll do is, here's the algorithm. If we have a case like this, and quotient is 0, so then we just pick a quotient 0, so we have now r equals to a. Or instead I'll just write this as r1 equals a, so indicating this number. So r1, this one is the same thing as q1 equals to 0, and so on, because now the q is 0. And then what we'll do is over here, if, so what we'll do now is do an if here, or just to ask the question, a is less than b right here. So if the number a is less than what we're dividing it by, for example 3 over 4, then we just stop, because that's just the remainder. So then we're done. So if yes equals done, else no, we just continue. Let's put no equals continue. So if it's not less than, we just keep going. And now what we'll do is now r2, and now we have q2 equals to 1 over there. Let's put these better like this: 0, q2 equals to 1, and so on and so forth. That's qk minus 1. Let's put this like, I was gonna put a q, but you get the picture. So now what we have is going to be, when we plug in 2 in, or a 1 in there, we have a minus b times 1, which is the same thing. A is just this value, r1. So this just equals to r1 minus b. And now since we're subtracting r1 by b, so we're subtracting that, that means that r2 is going to be less than r1, because we're subtracting by by b, like that. And now what we do is, if r is less than b, r2 is less than b, then we continue, then again done, else continue. And again, b is a divisor. If no, this is equal to continue, like that. No equals continue. So then we just keep going. Now what we have is r3, and that's q3, so this equals 2. This is going to be, plug that in, we have a minus 2b, which is the same thing as writing r1 minus b again. In other words, r2 minus b, and then this keeps going on. This is going to be r3 minus b, or this is the r4 equals to r3 minus b, and so on. So it keeps going on. So r of k minus 1 equals to this is rk minus 1 minus b. And now we have, in this case here, r3 is less than r2, and keep going on. We just if, else, etc. So if, and then we keep going. Now we have, at this point, r4 is less than r3, and keep going on. And then eventually what we'll have is, if we keep going until we have rk is less than b. And also this one here is the this is the qk value, because remember here, this is the number of the rows. So q1 is 0, q2 is 1, and then this one all the way down, q3 is 2. We'll move this over here. So we have qk equals to qk equals to k minus 1. Put an arrow like this, equals to k minus 1 as the value of it, because remember, just increasing by integer by 1. So thus what we have is, thus eventually we get is rk and a q value such that we have a equals to b qk plus rk, and this is all for I'll move this over to the left, all for zeros less than equal to rk less than b, like that. So we'll eventually get to this, and we are done. And that is the kth row like that. So yeah, I just moved everything to the left, and let's just circle this like that. So yeah, going further, so this proves the existence and also gives a simple division algorithm to compute the quotient and the remainder. However, this algorithm needs q steps, and this is not efficient. And again, this is from Wikipedia. I just changed up how the format was. I realize there's a line going through on the sides. But anyways, let's give a quick example here of one with actual values. So example here, and look at the case again. This is for a is greater than or equal to 0 and b is greater than 0, and so we just proved it for this case that it exists, and as I showed, they all the other ones can be reduced to this, so that is proven there. So let's just look at the example where the dividend and the divisor is equal to 9 over 2. So we're dividing 9 by 2, and again we have that formulation a equals bq plus r. And what we'll do is make that giant table like this number. So we have the number like this, and now we have the q values here. So number 1, 2, and so on. So the first one we have q is 0, and then we have the r equals 2 is rearrange this a minus b q, which equals 2. A is 9 minus, and now we have minus b is 2 times it by q now, and then we do our check, is r less than b, where b is equal to 2, and then put the question mark like that. So what we have here is r in this case is equal to 9 minus 0, r equals to 9 here, and then is r less than b? No. So we continue the next one. So we just add this one, add 1 to q, because remember just integer values, and this is always going to be q, and r is going to be positive for this case. Yeah, so r is going to be, r is equal to 9 minus 2 times 1, so that is, this is r1, so r2 is going to equal to, as I showed above here, that's just going to be, well, r the previous one, rk1, k minus 1 minus b. So this is going to be, what we can even look at is 9 minus 2, like that, which just equals to r1 minus 2. This just equals to 7. And then is r less than 2? No. R is greater than 2. So 7, in this case we have 9 is greater than 2, and we have 7 is greater than 2 there. Now we go to the next step. So we increase the q by, well, now it's 2 there. Now we have r3, I'll just write these down, instead of just writing that, I'm just going to write this now. This is going to be 7 minus 2, because we always subtract 2 from the previous one, or subtract b from the previous one. You could also see, put in brackets like this, just to show you, this is just the same thing as 9 minus 2 times 2, which equals 2, which equals 9 minus 4. Let's move this over. 7 minus 2 is 5, same thing as 9 minus which equals 2 like this, that equals to 4. 9 minus 4 is 5. So you could plug that in, or just do that one we just derived above, where you just subtract b from the previous r. So now we check, is r less than b? No, because 5 is greater than 2. So we continue the new one here. So 4, now value of q increased by 1 is 3. So now we have 5 minus 2 equals to 3. Is 3 less than 2? No, because 3 is greater than 2. And keep going. Next one is the fifth one. Now we have r's value is 4. We have 3 minus 2. This equals to 1. And yes, 1 is less than 2. And basically here is where we stop right here. So stop, put it in capitalized like that. Yeah, so thus what we end up having is this is equal to R5 and this equals to Q5. So thus we have is Q5 equals to 4 and R5, the remainder, equals to 1. And we can even see this, that the value A, now we have the B, or I'll just write A equals to 9. So 9 equals to, well, I should put that a first. So number a equals to b q plus r, and this equals to, well, a is 9, b equals to b, and b is 2. I should put it all under here. So we have 9 equals to 2 times 4 plus remainder 1. So that's just equals to 8 plus 1 equals 9. So that's check mark. So we've shown, that's just an example showing this existence of these values q and r. So we've gotten that right. So now let's look at the uniqueness of it, because that was just the existence. Remember, the second part is to look at the uniqueness of the values of q and r. And this is to show that the values q and r is always going to be completely unique whenever you have that case where r is going to be positive and less than b, or the absolute value of b. So the uniqueness, suppose, to prove this, suppose that we had other values. Suppose there exists other values, and we'll just go q, and another one q1, and then another one we'll have is as r and r prime, or q1 or r1. I'll just call those prime again. And then this is with, so we'll do with the conditions that we'll have r just is going to be positive greater than 0, but then we'll have r prime is less than the absolute value of b, and see if these can be different values. And then again, this is such that, so we suppose that there exist these kind of figures such that we end up having a equals to b q plus r, and also we have a equals to, because the one's always unique. So a b, just given. So those are a and b are given, the ones we're dividing, dividend by the divisor b. A equals b. Now we'll just do q prime plus r prime. So if we have these cases like this, and then this is with two different values like that, and now what we'll do is let's add, this is going to all make sense in a bit, so let's add the following inequalities. Inequalities right now, just to show what we're working with. Pretty interesting proof that I saw on Wikipedia. So we'll have r is going to be, let's say it's greater than or equal to 0, and it's less than the absolute value of b. Now if we look at the negative side of all this, let's just put another inequality. What we'll do is, now I'll put a negative absolute value of b. This is going to be, well, less than the negative of r prime, because remember r prime is just greater than 0. Everything has to go with this system there, and then where this is going to be less than or equal to 0. So we just flipped it around using the r prime like that, and then if we add these up, so we're adding, this will make sense in a bit. If we just add these up just to get some inequalities that includes r prime, and then the b. So if we just do this one, this becomes, well, negative absolute value of b is going to be less than, so we remove the equal to because this one is going to be, well, it's less than this one. It could be really, really small, or this one, this one could be really, really big, and so on, and there's at no point is equal to b there, so we remove that equal sign. So anyways, we put this here, so we add them up, so we have r minus r prime, and now this part here, add them up, is going to be less than b prime, and we put the less than because because this one over counters this one, because this can't equal to that, so then this one can equal 0, but doesn't change this part there. So we have this, but this just means that, well, thus what we have here is, this is the same thing as writing this, the absolute value of r minus r prime is less than absolute value of b. That's the same thing as writing it, because this value here is between the negative of b and less than the positive of b. So if it's positive, it's going to be less than it. If it's the negative of it, is going to be in between that. So it's in between the absolute value of it. So now what I'll do is I'm going to subtract these equations. So I'll write here, I'll put another arrow across like this. Subtract these equations just to develop more inequalities. Subtract these equations. So when we do that, what we end up having is a equals to bq plus r, and now we're subtracting it, or the other one is just a equals bq prime plus r prime. So let's just subtract these two out like this, so we get rid of this a, so we get 0 equals 2. Now we have here bq minus bq prime, and then plus r minus r prime, and that's so we can get this r minus r prime and this one here and work around with it to see what we could find out. Now if we factor this all out, or factor the b, we get b, factors out, we get q minus q prime, plus now we have this part r minus r prime, like that. And now this again equals to 0. So what I'll do now is I'm going to move this all the way to the other side and then put this over there. So what we get is r minus r prime equals, so now we have a negative b q minus q prime, and this one could just put the negative inside, and then we have b, and then it flips around, q prime minus q, like that. And now what's interesting here is that thus b is it divides r minus r prime, and I'll show you how this works, and this is actually pretty interesting. So thus this happens, and that's because, well, i.e. if you just look at this, move this around to the other side, we get, move the other one to the other side, this one over to the other one, we have r minus r prime divided by b. This just equals to q1 minus q. Yeah, so it divides it out like that. Very, very interesting. And now what we'll do is, well, let's look at this. Let's look at the case if r minus r prime is not equal to 0. So they're not equal to the same ones. And in other words, we have r is not equal to r prime, like that. So if we have this, so that's what we have is if we look over here, so look at, move this around here, this equation, well, this part here, r minus r prime, let's write this r minus r prime like that, and I'll drag this around all the way inside this one. So that's what we have is this equation, r minus r prime equals to b q prime minus q. Yeah, this implies that, well, this implies that b, the absolute value of b, is less than or equal to the absolute value of r minus r prime, like this. And that's because, notice here, this is this equals b times this part here, and basically that means this needs to be smaller in terms of absolute value. And you could see this as if you just move this around, move the q1 minus q on the other side. What we end up getting is, well, b equals to r minus r prime over q prime minus q. So it's a division of this. So this is just this value, but dividing it by this one. So the absolute value of it, whether it's plus or minus, it doesn't matter. It's going to be less than this value. And again, this is if we have q1, if q1 is not equal to q here. Because if it is, you're dividing by 0 and so on. And also here we're dealing with integers, so we're not going to have a fraction. We're going to have like 3 minus 2. For example, I'll just put another example, i.e. let's go with, if the difference here is 3 divided by negative 4, or actually let's put a different value, let's go with 2 minus 3 over 3 minus 4, whatever the value here, this is going to be, actually let's put another value here, 5, this is going to be 3, negative 3 divided by, here's negative 1, that equals to, let's put another number here, 5, let's just see it, so this is going to be negative 3 minus negative 2, this equals a fraction of it. But if we're dealing with integer values, this needs to change even more. I'll put this 6 like that, so that's going to be 2, and this is going to be 4, so the absolute value of this one is negative 4, and then this is going to be, well, this equals to 2. So in other words, absolute value of of 2 is going to be less than or equal to, I'll just put less than absolute value of negative 4, which is a difference, r minus r1, like that. Yeah, so that is what we have here, and I'll put this all in a giant bubble like that. But what we have here is another giant problem, but, and I'll show you if you haven't already picked up on it, here b is, if it's not equal to 0, then it implies that b, absolute value of b is less than absolute value of the difference r minus r prime. But if we scroll back up here, if we scroll up all the way here, when we did this inequality, we showed that b is greater than r minus r prime. So we can't have that. Yeah, so alright, I'll put the arrow all the way down. Where is that arrow? Like this. I'll put this down like this and keep going. Yeah, just keep going further and further over here. So what we have is, but, and also move it around, we'll have b on this side. B is greater than r minus r prime. So then what we have here, this is contradictory. So we can't have both of them there. So in other words, we can't have this not equaling to 0. So what we have is, if it's equal to 0, thus what we have is r minus r prime equals to 0, and then if it's equal to 0, we have r equals to r prime. And then what we have is this part right here is going to be absolute value of b is greater than just, well, 0. That's a 0. And then if we look at also now, we take this equation here. So that part there, this still satisfies it. So we have also b, and I'll write q minus, bq prime minus q equals to the r minus r prime. Now if this all equals to 0, well, if this one is equal to 0, then what we have is, well, what we have is on this other side there. So we have 0 equals to b q1 minus q, and this is only possible if, well, you can just divide b on both sides. We get, well, q1 minus q equals to 0. Just divide b out. In other words, we have q prime minus q equals to 0. I just wrote that. Q prime equals to q. Amazing. Yeah, so thus the only values that the other ones can be, it has to be equal to this one. See, we can't have different values. And we can write this out as, well, this proves uniqueness. Uniqueness. Or uniqueness of the integers. And I'll write q and r. Absolutely amazing. And now just to put a summary, thus what we have is when we're dividing, thus I'll write this down as a divided by b, or a divided by b like this with this slash, or there's different ways of writing divided, or a over b, or you could even write it as a and then divided by b like that, using that division, long division one like that. If we're dividing this and a and and basically and a, b are integers. This is just all a summary. Here I just added some more stuff. So summary of Euclidean division. So I'll write, instead of thus, write 4a divided by b, and then these many different forms of writing it. And a and b are integers, like this are integer, and I'll put a comma. There exists unique. So we have the exist part, which we proved, and then the unique part here. There, I'll put here unique, and then we could circle this one. So unique integers, q and r. Q and r such that a equals to bq plus r, and I'll just write with where r is positive and less than b. So r is greater than or equal to 0 and less than the absolute value of b, like that. And there is the Euclidean division statement of the theorem, like that. Very, very interesting. And hopefully follow along for this pretty extensive proof video, pretty long for something that seems pretty basic and elementary just by looking at it. But again, the arithmetic, if you look at it in more formal ways. This is pretty much how you're going to go about solving it, and is useful in a lot of division and computations and so on. And yeah, but overall you can just look at this one here and it's just all natural. Just in your head you could do this and so on. Anyways, that is all for today. If you learned from this pretty extensive derivation video, and yeah, like always, you can download these exact notes in the link below, and as always, you could view these on Steemit. I'll be uploading those shortly after, and make sure to check out my math forums, post any cool math or science related stuff you find. Anyways, all for today. Thanks for watching, and stay tuned for another math easy solution.